Consider a body of mass m. The sum of kinetic energy, K, and potential energy, V, possessed by the body is called the total mechanical energy of the body. Let this be equation 1. If a body is displaced due to a conservative force F, which is a function of displacement x, then from the work energy theorem, the gain in kinetic energy is related to the work done by such a conservative force F of x, and is denoted by the equation delta K is equal to F of x into delta x. Let this be equation 2. Let's now look at the relationship between this conservative force and potential energy. Let delta V be the change in potential energy. As F of x is equal to the negative of delta V by delta x, we get delta V is equal to minus F of x delta x. Let this be equation 3. Equation 3 expresses the relationship between a conservative force F of x and potential energy V of x. We know that mechanical energy is the sum of kinetic energy and potential energy of a system. So, by adding equations 2, delta K is equal to F of x into delta x, and equation 3, delta V is equal to minus F of x delta x, we get delta K plus delta V is equal to F of x delta x minus F of x delta x. Thus, delta K plus delta V is equal to 0. In other words, we can say that delta of K plus V is equal to 0. Let this be equation 4. Since delta of K plus V is the total mechanical energy, we can say from equation 4 that the change in total mechanical energy is 0 for a system all along its path. This is the principle of conservation of mechanical energy, which states that the total mechanical energy of a system is conserved if the forces doing the work on it are conservative. Let's now understand the principle of conservation of mechanical energy. Consider any 2 points A and B in the path of a body falling freely from a certain height h. According to the principle of conservation of mechanical energy, we can say that for points A and B, the total mechanical energy is constant in the path travelled by a body under the action of a conservative force. That is, the total mechanical energy at A is equal to the total mechanical energy at B. Or KEA plus V of x for A is equal to KEB plus V of x for B. Let this be equation 5. From the above discussion, we observe that work done by a conservative force is path independent. It is equal to the difference between the potential energies of the initial and final positions, and is completely recoverable. Also, as the work done by a conservative force depends on the initial and final position, we can say that work done by a conservative force in a closed path is 0, as the initial and final positions in a closed path are the same. Let's understand this with an example. Let's throw a body vertically upwards. In this example, we assume that the potential energy is only due to gravitational force, and we take the ground level as the reference level. The body thrown vertically upwards with velocity u has only kinetic energy at A and zero potential energy at A. Its total mechanical energy is expressed by half mu square. Let this be equation 6. At point B, the body possesses both potential and kinetic energies. The potential energy is mgx and the kinetic energy is half mv1 square, where v1 is the velocity of the body at position B. Total mechanical energy at B is denoted by equation 7. Using the equations of kinematics, we get v1 square minus u square is equal to minus 2gx. Simplifying, we get the expression for v1 as v1 square is equal to u square minus 2gx. Let this be equation 8. Now substitute equation 8 in equation 7. And upon simplifying, we get total mechanical energy at B equal to half m into u square minus 2gx plus mgx, which is equal to half mu square minus half m into 2gx plus mgx, equal to half mu square minus mgx plus mgx. Thus we get the total mechanical energy at B equal to half mu square. Let this be equation 9. When the body reaches point C, that is, the maximum height, it has only potential energy and zero kinetic energy, as the velocity at this point v is 0. Its total mechanical energy at C denoted by mgh. Let this be equation 10. We learnt earlier that the maximum height h reached is denoted by the expression u square by 2g. Let this be equation 11. Substituting equation 11 in equation 10, we get the total mechanical energy at C is equal to mg into u square by 2g. And on simplifying, we get the total mechanical energy at C is equal to half mu square. Let this be equation 12. We see from equation 6, 9 and 12 that the total mechanical energy at all points along the path of the body is the same. Hence, mechanical energy is conserved at all points along the path. Now let's look at another example. The individual on the bike shown revolves in a vertical circle of radius r. The individual along with his bike is considered to be a system. We assume that the potential energy is only due to gravitational force, and we take ground level as the reference level. At its lowest point, which is taken as the reference level, the bike possesses only kinetic energy but no potential energy. Let it be assigned a horizontal velocity u at the lowest point A. At point A, the total mechanical energy of the system is denoted by the expression half mu square. Let this be equation 13. When it is at horizontal position C, its velocity is v1, and the height of C from the reference level is equal to r. When at C, its total mechanical energy is partly kinetic, which is half mv1 square, where v1 is the magnitude of velocity at c and partly potential, which is mgr. The total mechanical energy at c is denoted by half mv1 square plus mgr. Let this be equation 14. When it reaches the highest point B, it has velocity v, and its height with respect to the reference level is 2r. It has maximum potential energy, which is mg into 2r, and least kinetic energy, which is half mv square. The total mechanical energy at B is denoted by half mv square plus mg into 2r. Let this be equation 15. As the individual moves on the bike, which is together considered a system, in the circular path, a centripetal force Fc, denoted by mv square by r, acts on the system. At position B, weight mg and normal force Fn provide the necessary centripetal force. When the speed at position B is decreased, the centripetal force decreases, and hence the normal force. To complete the motion along the circular path, the speed at B should be minimum such that the normal force on the bike is 0. Thus, mv square by r must be provided by mg, which is denoted by equation 16. Simplifying for v square, we get v square is equal to gr, or v is equal to the square root of gr. Let this be equation 17, which indicates the minimum velocity at B required to complete one revolution of the vertical circular path. According to the principle of conservation of mechanical energy, the total mechanical energy at A is equal to the total mechanical energy at B. Thus, half mv square plus mg into 2r is equal to half mu square. But since v square is equal to gr, substituting the minimum velocity at point B, v is equal to the square root of gr in equation 15. We get half mgr plus mg into 2r is equal to half mu square. On further simplification, we get half mg into r plus 4r is equal to half mu square. Thus, we get u square is equal to 5gr, or u is equal to the square root of 5gr, where u is the projection velocity at A. Let this be equation 18. Thus, from the earlier examples, we see that according to the principle of conservation of mechanical energy, energy can neither be created nor destroyed. It can only be transformed from one state to another. Consider a block attached to a spring placed on a smooth horizontal surface. The other end of the spring is attached to a rigid wall. The position at which the spring is at rest initially is considered to be the mean position, with no displacement of the spring. Then, the spring is compressed and released. You can observe the spring oscillating to and fro from the rest or mean position. The displacement of the block is always measured from the mean or rest position. The spring here is under the action of a variable force, known as the spring force, which always acts towards the mean position or in the opposite direction to the displacement. When the spring is stretched, the displacement is positive. When the spring is compressed, the displacement is negative. The spring force is the restoring force which is responsible for bringing the block attached to the spring back to its mean position. The spring force F is directly proportional to the displacement x from the mean position. Thus, we see that the spring force F is proportional to minus x. We say minus x as the spring force is always directed opposite to the direction of displacement. Or spring force F is equal to minus kx, where k is the spring constant. Let this be equation 1. In equation 1, F is equal to minus kx, which represents the force law for the spring known as Hooke's law. Work done W by the spring force is denoted by the expression integral F dx in the limits 0 to xm, where xm is the maximum displacement of the spring. Let this be equation 2. Since the spring force F is equal to minus kx, we get W is equal to minus integral kx dx in the limits 0 to xm. Let this be equation 3. On integrating equation 3, we get W is equal to minus k into x square by 2 in the limits 0 to xm. Thus, we get the work done by the spring force equal to minus half kxm square. Hence, the work done by the external elongating force will be plus half kxm square. This is the work done by the external elongating force against the spring force, and hence is stored as potential energy in the spring, as given by equation 4. Work done by the spring force can also be calculated by the area covered under the graph of displacement x during elongation or compression taken on the x-axis and the corresponding spring force F taken on the y-axis. The area of the shaded portion indicates the work done by the spring force. In equation 3, W is equal to minus integral kx dx in the limits 0 to xm. We know that the initial displacement is 0 and the final displacement is xm. Instead, if the initial displacement is x1 and the final displacement is x2, then the work done W by the spring force would be equal to the negative of integral kx dx in the limits x1 to x2. Let this be equation 5. Then the work done by the spring force will be equal to half kx1 square minus half kx2 square. Let this be equation 6. Equation 6, where W is equal to half kx1 square minus half kx2 square, indicates the work done by the spring force. Then the work done by the external force W will be equal to half kx2 square minus half kx1 square. Let this be equation 7. Now if the spring is compressed to x2 and brought back to x1, then the work done by the spring force according to equation 7 will be half kx1 square minus half kx1 square, since the final position is the same as the initial position. Then, the work done will be equal to 0 as in equation 8. This proves that the spring force is a conservative force since the work done for a closed path or round trip is 0. Thus, we define the potential energy V of x of the spring as 0 when the system of the block and the spring is in equilibrium position. For any extension or compression x of the spring, we have V of x is equal to half kx square. Taking the derivative of the equation of potential energy of the spring, we get minus d by dx V of x is equal to minus d by dx half kx square. On further simplification, we get f of x is equal to minus half k into dx square by dx. Thus, by doing the derivation of the equation of potential energy of a spring, we can easily verify the equation for the spring force as f of x is equal to minus kx as shown. According to the work energy theorem, the work done by a net force on an object is equal to the change in its kinetic energy. That is, F delta x is equal to delta k, where F is the net force, delta x is the displacement, and delta k is the change in kinetic energy. Let this be equation 9. Now, if the forces acting on the body include both a conservative force Fc and non-conservative force Fnc, then the equation 9 can be written as Fc plus Fnc delta x is equal to delta k. Let this be equation 10. Simplifying, we get Fc delta x plus Fnc delta x is equal to delta k. Since Fc delta x is equal to minus delta v in equation 10, we get minus delta v plus Fnc delta x equal to delta k. Let this be equation 11. We have Fnc delta x equal to delta of k plus v. Let this be equation 12. Since k plus v is the total mechanical energy of the body, which is the sum of the kinetic and potential energy of the body, equation 12 shows that the work done by the non-conservative force is equal to the change in the total mechanical energy of the body. Some forms of energy that we will deal with in this module are heat energy, chemical energy, electrical energy, and nuclear energy. Now, let's understand heat energy first. When satin cloth pieces are rubbed against each other, due to friction, sufficient heat is produced to make the hands feel a rise in temperature. The rise in temperature is due to the rise in internal energy of the body. Here, the satin cloth pieces. Consider that a body is given a push and is then released. When it comes to rest, all its kinetic energy is lost, and a part of this kinetic energy is converted into heat, and the remaining is lost in doing work against the friction. to overcome friction. There is a slight rise in the temperature of the surfaces in contact. Let us look at another form of energy, chemical energy. Chemical energy is produced when the molecules of the reactants participating in a chemical reaction combine to attain greater stability by forming stable compounds. The burning of any form of fuel is a chemical reaction. Burning is an exothermic chemical reaction where the chemical energy of the reactants is mainly converted into heat energy, which can later be manifested in other forms. Thus, in an exothermic reaction, the energy of the reactants is greater than that of the products. Hence, exothermic reactions like combustion of fuels are indispensable in catering to our daily energy needs. There are some other chemical reactions that absorb heat during their reaction and are called endothermic reactions. Some reactions, such as photosynthesis, are endothermic reactions which allow plants to make sugar from carbon dioxide in the presence of air. Chlorophyll acts as a catalyst in the process of photosynthesis. In this case, the energy required for the reaction comes from sunlight. Now, let's understand electrical energy. Electricity is the most convenient form of energy. Electricity is a manifestation of electrical energy and is responsible for running many of the devices in our daily lives, such as electric bulbs, fans, grinders, etc. Till the late 19th century, physicists were of the view that the mass of an isolated system remains constant and it is conserved. They believed that matter can be neither created nor destroyed. It can only change from one form to another. For example, when water is frozen, it turns to ice. The ice melts to water, and when water is heated, it turns to vapor. In all the three forms, the mass of the system remains the same. However, Albert Einstein proposed his famous mass-energy equivalence relation. E is equal to mc square, to show that mass and energy are equivalent. In this relation, E is equal to mc square, and c is the speed of light in vacuum, which is approximately 3 × 10⁸ meters per second. Thus, according to Einstein's mass-energy equivalence relation, mass and energy are equivalent to each other. Mass can be converted into energy and vice versa. When a mass m is destroyed completely, the equivalent energy E is produced. Thus, according to Einstein's mass-energy equivalence equation, 1 kilogram of matter can produce a humongous amount of energy, which is E is equal to 1 × 3 × 10⁸ square joules, equal to 9 into 10 raised to 16 joules of energy. The energy produced by 1 kilogram of mass is equivalent to the annual electrical energy produced by a power generating station. That is 3000 megawatts. Now, if 1 gram of mass is completely destroyed, the energy produced is expressed as E is equal to mc square. That is equal to 0.001 into 9 into 10 to the power of 16. That is equal to 9 into 10 to the power of 13 joules. One of the most expensive forms of energy is nuclear energy. Nuclear energy is energy derived from a nuclear reaction, such as nuclear fusion or nuclear fission, from which energy may be released in accordance with Einstein's mass-energy equivalence relation. In nuclear fission, a heavy nucleus like uranium-235 absorbs a slow neutron and hence splits into lighter nuclei. The final mass of products is observed to be less than the total mass of the reactants, and this difference in mass is known as mass defect, denoted by delta M. The mass defect delta M is converted into energy in accordance with E equal to delta M into C square. In a nuclear fusion reaction, lighter nuclei fuse to form a heavier nucleus. This fusion is accompanied by the release of a large amount of inherent energy in accordance with the mass-energy equivalence relation. In nuclear fusion too, there is a mass defect which accounts for the amount of energy released according to E is equal to delta M into C square. The source of the massive amount of energy released by the Sun and the stars is believed to be due to a nuclear fusion reaction, when isotopes of hydrogen, namely deuterium and tritium, undergo fusion to form an isotope of helium and a neutron with the release of a large amount of energy. The energy released is due to the conversion of a mass defect between the reactants and products in the reaction. The law of conservation of energy states that the total energy of an isolated system is always conserved and that energy can only be transformed from one form to another, but can neither be created nor destroyed. For example, when a firecracker explodes, the chemical energy stored in it is converted into light, heat, and sound energy. Nuclear energy is used to produce electrical energy in a nuclear reactor. Different forms of energy are used to do work. Earlier, we learnt that work is said to be done when a force F acting on a body displaces the body through D in the direction of the force. When work is done, energy is transferred. The rate at which work is done or energy is transferred is called power. Thus, power P is equal to work done W by time T. Instantaneous power P is equal to dW by dt. But dW is equal to F dot dr, where dr is the displacement. Therefore, P is equal to F dot dr by dt, which is equal to F dot V. Since dr by dt is equal to instantaneous velocity v. Power is a scalar quantity and its SI unit is watt, and its dimensional formula is m power 1, L power 2, T power minus 3. Power can be expressed in horsepower denoted as HP, and 1 horsepower is equal to 746 watts. The commercial unit of electrical energy is kilowatt hour denoted as kWh. 1 kilowatt hour is equal to 1000 watt into 1 hour, and which is equal to 1000 watt into 3600 seconds, and is equal to 36 into 10 to the power 5 joules.